Welcome back to another explainer. Today, we're tackling an absolute nightmare of a problem in polymer engineering, color matching failures. Look, if you've ever spent 10 minutes on a compounding floor, you know exactly the headache I'm talking about, right? So we're going to jump right into the actual science of pigment dispersion, looking at agglomeration, the real markers of dispersion quality, and exactly how to troubleshoot these issues when they inevitably pop up on the line.
Let's start with a scenario that might hit a little too close to home. Picture this. You've got the world's absolute best pigment. Your formulation? Flawless. You're running the most advanced machinery money can buy. But the final color still comes out completely, entirely wrong. It just fails. So what's the deal? Well, human nature is to immediately blame the pigment selection. But actually, the vast majority of color matching failures in our industry come straight down to poor dispersion. It is not the pigment itself, it's how it's being handled in the melt.
Here's our roadmap for this explainer. We'll quickly define what dispersion actually is, break down pigment particle structure, look at the processing factors affecting quality, run through evaluation methods, and then wrap up with some real-world industry troubleshooting cases.
All right, part 1. What exactly is pigment dispersion?
Think about something as basic as making a cup of tea. If you dump sugar in and it doesn't dissolve properly, you get a completely uneven taste, right? Bitter sips at the top and then just overwhelmingly sweet sludge at the bottom. Well, pigments and polymers behave the exact same way. If that pigment isn't distributed uniformly, your final color is going to be completely unpredictable.
So what's actually happening at a physical level? When pigments are first manufactured, their particles naturally like to stick together into these clumps. We call these clumps agglomerates. The whole name of the game in color compounding is to break these specific agglomerates apart so we can distribute that color evenly.
Moving into Section 2, Pigment Particle Structure Explained.
Okay, there are 3 distinct levels of pigment particles, and knowing the difference here is absolutely critical for the compounding floor. At the top, we have the primary particle. That's your smallest, most basic individual unit. Right below that in the middle row is the aggregate. Now this is a tightly bound, permanent group of primary particles. Your processing goal here, never ever try to break these. You just can't. Finally, at the bottom, we have the agglomerate, which is a loose cluster of aggregates. The big takeaway here is that our machinery must be dialed in specifically to smash apart those loose agglomerates, but leave the permanent aggregates totally intact.
If we mess this up and fail to break those agglomerates, the results are instantly painfully visible. You're going to see a whole host of defects: ugly black dots, prominent color streaks, an uneven shade across the batch, super low color strength, and even physical surface defects and gloss variations. And you know what's really frustrating? When these symptoms pop up, operators almost always jump to blame the pigment's overall quality. But the reality, the pigment is usually completely fine. It's the dispersion process that dropped the ball.
Let's head into Section 3 and look at the actual factors affecting dispersion quality.
Looking first at the material factors, it's basically a massive balancing act. Take pigment type, for instance. Organic pigments are notoriously a headache to disperse compared to inorganic ones. Then you have particle size. Smaller particles will absolutely give you a much better, richer color strength, but, and it's a big but, they're significantly harder to disperse evenly. Luckily, if a pigment has undergone surface treatment, it allows for way easier wetting, which sets you up for fundamentally better dispersion right out of the gate.
Beyond the raw materials, we have the processing factors. These are the dials we actually control on the floor. Finding the perfect operational balance is a must. If your temperature is too low, your dispersion is garbage, but if you push it too high, you literally degrade the pigment. As for screw RPM, run it too low and you don't get enough shear force to break those agglomerates. Run it too high and yeah, you get better mixing, but you generate excessive damaging heat. Honestly, dialing in the proper back pressure is the real secret sauce here to getting that optimal mixing and color uniformity.
All right, Section 4, Dispersion Evaluation Methods. How do we know we're doing this right?
You essentially have a 3-step escalation for testing this. Step 1 is just your basic visual check, eyeballing the product for dots, streaks, or a rough finish. Step 2 takes things into the lab with microscopic evaluation, where you can literally see if those pesky agglomerates are still clustered together. But Step 3 is the heavy hitter, the filter pressure test. This is the gold standard for the masterbatch industry. As your polymer flows through a filter, if the pressure suddenly spikes, it means unbroken agglomerates are clogging up the screen. Simply put, high pressure rise equals poor dispersion.
So what do you do if your filter pressure test shows terrible results? You don't just scrap the batch. You run through these 5 actionable techniques. You can pick a better carrier resin, tweak to the correct screw design to adjust your shear, optimize that processing temp, or throw in some dispersing additives. But I really want you to pay attention to number 5, Optimizing your pigment loading. There is a golden rule in this industry. Overloading your polymer with pigment will massively, and I mean massively, increase your risk of pore dispersion. You just can't force it.
Let's bring all this theory to the floor with Section 5, Industry Troubleshooting Cases.
Case number 1. You're inspecting a black masterbatch, and you spot these little black dots scattered all over the surface. The root cause? It's almost certainly unbroken carbon black agglomerates. The direct fix here is purely mechanical. You've got to ramp up the mixing and apply a higher shear force from your machinery to physically rip those tough clusters apart.
Now, case 2. Say you're looking at your output and you're getting these red shade streaks, just inconsistent lines of color. That usually points to a chemical interaction issue, specifically pore pigment wetting. To fix this one, you'll want to add a dispersion additive to help the polymer actually coat the pigment while simultaneously optimizing your temperatures so everything flows and mixes the way it should.
And for our third case, what if your color strength is just generally low? It looks weak, washed out. Well, that means you have incomplete dispersion across the entire batch. The agglomerates aren't necessarily forming huge visible dots, but they aren't fully broken down either. There's no single magic bullet for this one. You literally need to do a full review and improve your overall compounding conditions. Double-check your RPM, your back pressure, and your temperature profile.
This perfectly brings us to an ultimate industry truth. Pigment quality is important. Absolutely, no one is denying that. But dispersion quality? It's even more important. Listen to this. An average pigment with excellent dispersion will almost always outperform a premium, super expensive pigment that suffers from poor dispersion. It's not just about what you're buying, it is entirely about how you process it.
We've covered a ton of ground today, from the microscopic structure of a tiny agglomerate to twisting the exact dials on your compounding machinery. Now that you understand why dispersion is the absolute backbone of color quality, I want to leave you with this. How are you going to apply these specific checks and balances on your own factory floor tomorrow? Will you look at that next bad batch and blame the pigment, or will you look at your shear rate? Think about that. In our next explainer, we're diving deep into additive masterbatch formulations, talking UV stabilizers, antioxidants, and slip additives. Until then, keep optimizing those processes.
So now you know that excellent color isn't just about choosing the right pigment, it's about breaking agglomerators, achieving perfect dispersion, and controlling the entries. Processing cycle. A small mistake or dispersion can lead to color variation, poor mechanical properties, black speck, and a customer complaint. But here's something even more interesting. In the next video, we will dive deep into dispersion testing method, how professionals evaluate dispersion quality using a visual analysis, microscope techniques, filter pressure test, and a practical production method. You will learn how to identify pure dispersion before it becomes a costly production problem. If you are serious about becoming an expert in masterbatch polymer compounding, color matching, and plastic processing, make sure you subscribe to the channel and turn on the notifications so you never miss an episode. If you found this video valuable, hit the like button, share it with your colleagues, and let me know in the comment what is the biggest pigment dispersion problem you face in your production. I will answer your question in upcoming video. Thank you for watching. Keep learning, keep experiment, and I will see you in the next video. This is a Secret Polymer Tech where polymer science meets industry practice. Thank you.